All right, hello everyone. I'm your faculty member for cs300 data structure and algorithm class. This is week 2. In this week's module, we are going to talk about different algorithms, and in particular, the sorting algorithms are really classical ones that shows you how different algorithms will have a different running time. So in this section, I'm going to demo what's a Quicksort and how Quicksort works. So Quicksort is a sorting algorithm that uses the divide and conquer strategy, which is commonly used in computer science. So what a divide and conquer means is you divide the problem into a smaller steps, and you repeat, and you can solve the problem in a smaller set, and then in all you can solve the whole problem, right? So so Quicksort, the idea behind the Quicksort is basically you divide an array or a list of numbers, okay, or data, whatever, that's solvable, right? You can compare, one data to another. You can compare the values, then you can sort them. All right, so then you divide into 2 partitions, right? So the key is to how do you partition the array into subarrays. And so for any given array or subarray, you can pick a partition. There's a lot of different algorithms to pick partition. Let's say in this example, we pick the middle point, and then for all the numbers that's less than, say it's 7, right? For all the numbers less than 7, I'm gonna put the number in the left side, and for all the numbers is greater than 7, I'm gonna put it on the right side. So the idea is after each iteration, the pivot point, we call it, in the middle or roughly in the middle, are in its right place. So it's the final place for that pivot number. So every time you do a round of sorting or partitioning, at the end, the idea is at least one number is fixed, right? So you know the final position for that number. And then you can recursively sort the left-hand side and right-hand side to the pivot number. There's 2 subarrays. And if you can do, if the left-hand side is sorted, right-hand side sorted, and all the number on the left-hand side is less than the pivot number, and all the number on the right-hand side is greater than pivot number, then all the arrays are sorted. Okay. So there's some key details about how to write a Quicksort algorithm. The idea is simple. However, to write it correctly the first time is difficult because there's a lot of details that you need to think about. So let's take a look at the example. Okay. Replit.com, by the way, is a very good online IDE that you can use to, if you don't have a local IDE, you can use this to basically prototype your code, and it will be easily, you can share the code with others using the URL as well. So this is a good website. Okay, so let's start some examples, right? So let's do a vector example. Okay. Okay, so let's let's say Quicksort demo. Okay, and let's give a sample test vector of integers, right? And I'm gonna copy paste some existing data set, right? So make sure you have enough data size to debug it, right? So it has negative numbers, big numbers, small numbers, etc. Okay, and then I'm gonna so before sorting, I'm gonna print out the number, right? So I have an iterator that points to that vector. This is an EDN that you should be familiar with. And okay, so iterator print pointer to the IT iterator and comma. Okay, and then I'm gonna have a new line at the end of that. Okay, so and then I'm gonna define a function called Quicksort, which takes 3 arguments. One is the array itself, it's a reference to the array, and the beginning index for the number, the first number in the array, and then the last number in the array. So basically it's array size -1. Why -1? Because it's 0 base index, right? And then after sorting, I'm just gonna copy paste this. Of course, ideally in the good practice, don't repeat yourself. You can put it into a function, print. I'm gonna just be copy paste for now. All right, so we set up this test first, and then we're gonna implement the Quicksort, okay? So again, it takes 3 parameters. One is the vector of integer. Let's call it data. Again, it's by reference. And I have a begin and the end index. Okay, cool. Now, so how we start with the Quicksort? Well, we could, first of all, let's check the boundary conditions where if you have no data or it's only one element. In other words, if the beginning index is equal to or greater than even the end index, that's base case, right? I'm going to just return because there's nothing to sort. Only one element or no element. You don't need to do anything, just return. So now you have at least 2 elements and we can sort it. So I'm going to get int p equal to partition. So I'm going to do a partition. I'm going to have a new function which returns the partition. Remember the pivot point, the partition of that index, index into that array, which is the final version, right? And in that, we're going to sort and find out what is the partition for this array. And once you get partition, you can just recursively call Quicksort with the new range. So remember the pivot to the left is from the beginning to the partition, and you can sort to the right of the partition, which is the p+1, and okay, so you can recursively solve these two. Because this is a like binary search, every time you divide this problem in half, so this is like log n of O of log n. If you understand big O notation, we're gonna talk about big O notation in a different video. Okay, and then overall, because you have to do it n times, so the overall algorithm is n log n. Now, of course, this is a average case, but if you are very unfortunate, your array is already sorted in some order, and every time you pick the smallest one, the pivot, then the worst case you have n2 n squared running time. So Quicksort, worst case is still n squared, but average, I guess you can achieve n log n. All right. So anyways, so again, this is the overall algorithm. Now let's implement this pivot function we call partition, and we return an integer with a partition, right? So again, it takes a vector of int of data and begin and end. All right. Okay. So how to deal with a pivot? Partition. Again, I'm gonna set low and high. Okay, and then I'm gonna select the pivot number is equal to the data of low plus, so I take a middle point, right? So high minus low divided by 2. Why I'm doing this? Why not just the low plus high divided by 2? Now this is the details, right? Again, if the number is very big, and this are integers, and C++ integers have a maximum range, right? Depends on the machine. You can have 4 bytes, 8 bytes. And anyhow, it could be so if you have 2 big numbers add together, it can overflow. It can exceed the biggest number of integers, and you will have trouble. But if you do this way, it will guarantee to be within an integer range because you're taking the middle, right? So it's less than high. All right. So this is one detail that you need to pay attention to. Now, while not done, I'm just saying there is a condition. Now, what is that condition? Okay, let me come back to later, right? So not done. Then, so you will actually look at the data from the low end. If the data to a pivot, so you have a pivot number, right? So if the data sort of from the lower end is smaller than the pivot number, that's a correct way, right? You want the number to the left of the pivot number smaller. So if this is the case, okay, if data at low pointer is less than the pivot number, okay, I'm gonna just increment low. So basically I'm looking for the next data until it's not the case, until it's greater than or equal to the pivot number. Then I stop, right? Now I'm also at looking at high end, and normally it should be greater than pivot, right? And that's where the high end number should be at the end of the round. And if that's the case, I'm gonna just subtract high. And so these 2 pointers will be in the middle ideally, right? So once them all stopped, that's where I need to swap the low and high. Okay. Now I still need to be careful that low is still then less than high. Now this is actually our condition. So if low is as long as low is less than high, I can continue, right? If low is greater or equal to high, that means you have exhausted. Let's say so the 2 pointers swapped, right? They crossed each other, and that's where you have 0 numbers left in the array that haven't been compared. Okay, so if that's still the case, I'm going to swap low and high because the number should belong to the other side of the pivot number. So the swap actually in the vector, there is a swap function that takes the 2 data and swap them for you. So you don't need to worry about the pointers and stuff. So now, but the caveat is you need to remember, or the Google search the what's library function that has a swap. Used to be C++11 before it's in algorithm, but now it's called utility. Okay. C++, and you guys are hopefully all using C++11 or later, 17. Okay, so this is swapping the two data. And then the good thing about the swap is not only it's a simple data integer. If you have an object like what's in the assignment, you can still use this to swap to complex data, right? Structured, because you're swapping pointers. So now don't forget, after you swap it, you can continue advance the pointer, the left pointer and the right pointer, low and high. So it will keep going, continue to do this logic. All right. So now that's now what are you going to return at the end? Well, at the end of the big while loop, your low and high crosses, and I think you're going to return high, right? Because low is equal to high, doesn't matter, or low is greater than high. This kind you return the high. All right. So that's it. So basically, the important thing to remember is at the end of each partition action, this P is P is the final location, final index for the pivot number in the sorted array. So after sorting, this is the final position. Every time you do this partitioning, you actually located one number. So you have to do it n times and such. Okay. So now I think that's pretty much. Let's run it. Hopefully it will work. Let's see. Okay. So before it's this number, and after you can see, yeah, they are pretty much sorted. Okay. And if you still have some questions, then you can just read again the Zybooks chapter 3.18. It will give you another exercise. So so that's the Quicksort. Now let's look at the assignment. Okay. Basically, you go to the website and you go to learning modules. We're in week 2, so you go to module 2. And you look at you're gonna do your Zybooks and assignment, click on vector sorting. You need to look at the rubrics, right? And if you click on requirement rubrics, you can see the overview. Basically, this project, right, will give you some sales data from like a big company like eBay or whatever. And there's a lot of data in it, right? Like this data has, 12,000 bits. And you also have a smaller set for that December only 76 bits, so you can play with smaller data sets for now. It already have some predefined code written for you. It will show a menu or text-based application. It have these menu options. Your job is to implement manual 3 and 4, selection sort and quicksort. I haven't talked about selection sort yet, but I will talk about it. Okay. So once you implement the selection sort and quicksort, you're gonna run them and compare how long it takes for each algorithm to run for the same data sets. Okay. So here is some prompt. You want to look at those informations and then click on the zip file. I already have that downloaded. The zip file contains all the data, all the initial starting code that you're going to start. Now, before we go into the code, I want to remind you the rubrics, right? So I'm looking for, so not only you need to implement this function and make sure it runs correctly, and you tested and submitted the source code. By the way, I only needed one CPP file. You don't need to submit the whole zip folder. because I have the rest of the folder. You only need to submit the one single file that you implemented, the C++ file, and that's it. And I can run it against the some standard, you know, project folder. Okay, so don't submit the zip folder. All right, and then you, in addition to that, don't forget you need some code reflection. Right, this can be in your Word format. Right, you can it's separate format than your C code, or C++ code. Describe the purpose of code, the technique implemented to solve a problem, challenge encounter, and approach to basically your thought process, how you approach a problem, what roadblocks you have encountered, and how you solve them. And then don't forget that you have to do a pseudocode, a flowchart. One of them, you don't need to do both. You're welcome to do both, but you know, pick one of them. And you know, in chapter 1, you are if you forgot about how to do pseudocode flowchart, go back to chapter 1 and review it, right? So basically, supposed to have some pseudocode, the flowchart for the key algorithm. You don't need to do for the whole entire program. You only need that for the quicksort and selection sort algorithms. Okay, how this is implemented, and the rest of them is basically on your code itself. I'm looking for the correctness, of course, and some, you know, readability and notation, and you know, comments and stuff to that, and functionality and such. So yeah, read the rubrics. Okay, suppose you download the zip, right? You unzip it. So you will be end up with here. No, not this. Yeah, this. I'm using a VS Code. You can use any IDE you want, right? So in the VS Code, you can see you zip into folder. It's called the cs300 vector sorting, and in that folder, you can see there is a bunch of CPP file, helper files, and such. So the main the starting code is in the vector sorting, the CPP file, and then and you also have this data in your directory. If you look at the data, you can see there's comma delimited numbers, and you're supposed to, you know, read the data from the file and parse into a data structure we call bits. Right, the bits have some field, and you want to fill them all, and then yeah. So if you open that vector sorting CPP file, you will see. First of all, put your name here, right? Put your name there, right, John? So I know it's your code, and then you can see it will include the CSV parser GPU. Make sure it's there in the same folder. It will use that to compile the final binary, right? And it will give you all the. Wait a second. Go back to this. So there's some helper function already defined for you. The bit data structure is also defined for you. You have basically 4 fields, right? The amount is a double, rest of the bit ID title is the string. And in this case, you are sorting not by the amount, but the title. So it's a string comparison. It's instead of a number comparison. Okay, so and you can scroll down to the sorting. So selection sort and quicksort. Okay, and then in the main function, there's some options here. You're supposed to implement. Just look for all the fixed me, right? You have to fill all the fixed me, and then you're done, right? So case 3. Case 3 is the what is this? Selection sort, right? So suppose you already implemented selection sort, and then you want to call selection sort, right, with your bits. Okay. Now, before you do that, you want to time how long it takes. So there is a ticks variable that for you. You call the clock function. Okay, and And then after that, you call the clock function again. Update ticks minus ticks. So basically, you calculate the number of ticks between these two, right? And then you can convert that to seconds, right? How to convert to seconds? You can say something like time spent, right? And use this formula, number of ticks times 1.0. It's a floating number, and divided by there is a micro called clocks per second, right? That's the micro defined and seconds. Okay, so basically you convert that time spent to second. All right, so don't forget that you need to break, otherwise it will spill into a next line, next case. All right, so same thing for case 4. So very similar, you can even copy and paste, but number 4 is for another sort, Quicksort, so different sort, okay? But Quicksort needs additional arguments, which is from 0 to initially bits dot size -1, again, 0 based, right? So that's the Quicksort bits, not binds, sorry. Okay, so here's some, you need to do these two. And then now you have to fill out the details on these two sorting, right? Selection sort is very simple. You can basically the idea of selection sort is, and then this is hint. So you have 2 for loops, right? The outer loop will go through the list once, and for each numbers you go through, you are selecting the minimum numbers, okay, and put it into the first position, and then the first position is fixed, and then you keep sorting the rest of the arrays, other than the first one, and the second one is fixed, and third one's fixed until all the lists are sorted. So basically a double loop. So it's about the complexity is about O(n) squared. Okay, power 2. Okay, now just want to quickly give you a well, since we already talked about Quicksort, it's basically the same as what I demonstrated to you. Let me give you a quick rundown of the selection sort. So see, this is already give you a lot of hint. You can check the size of bits vector. Size T is basically a machine dependent neutral, size equal to bits dot size. Right. So get the size of the data, and then loop through it. Right. For loop. You can use size T. Position to 0, starting from 0's position, and until it's size -1, again 0 based, right? Plus position, and then this is outer loop, and then you want to define a another thing, minimum for each round. So if minimum starting with the position, and then the inner loop, you can have a index called j is equal to position +1, right? You're comparing it with all the numbers after you, right? Because previously these are all sorted, so until size -1 and plus j. So that's inner loop. In the inner loop, you're comparing the two titles. So if bits of j. That's the number. Title. Remember, you're comparing a title, right? And then string compare. Remember, there is a compare function with another string. The minimum is the default is current. You compare the new data with the minimum. If less than 0, that means it's less than the minimum. The minimum will be updated to that index, right? Is that correct? Is that clear? So you're looking at all the numbers that after this current position, right? And then you just pick the minimum. If the minimum is still the same, that's fine. Otherwise, you have to swap them. Okay. So after this inner loop, let's say, is the minimum changes? If the minimum position not equal to the initial position, which is POS, then you're gonna swap, right? Again, you can use standard swap. Don't forget to import utility. So bits at position and bits at min. So you're gonna swap these two. All right. Of course, you need to include what? Utility, right? So utility.h utility, so you can use the extended swap. Otherwise, you have to implement your own swap. So that's pretty much for the quick selection sort. Okay. For Quicksort, now of course, I recommend that you run it before you move on, right? Make clean. I have a make project and just run bid. Okay, one load bits and display all the bits and selection sort. See, it takes 339 clock ticks, very small. But if you load the big data, for example, bid, you can load ebid sales.csv. That's a pretty big data. You can see it loads the data and all the data. There's and then if you do selection sort, it takes a while to finish, right? This is O(n) squared inefficient algorithm. You can see it takes 3.59 seconds to finish. So do we have a better way of it? Yes, we do. We have a Quicksort. So again, I have demonstrated how to do the Quicksort. You can follow this this hint, right? But because this is a week 2, a lot of you have some just getting started with C++ yet. So I'm gonna give you a rundown for that. Okay, so first of all, still pick the midpoint. Okay, and then again, if begin is greater than end, greater equal to end, that means I don't need to sort. It's already done. It's only have 1 or 0 element and just return. That's base case, because this is a recursive function, right? If you don't know what a recursive function is, you can review it. And then the partition. Well, I like to make it most just P, right? P is partition bids begin and end. So begin, you do the partition, and then after the P is fixed, you can do Quicksort 2 subarrays. One is from begin to the P, and then Quicksort bits from P+1 to end. So you just divide and conquer, right? Divide and conquer. All right, so that's the Quicksort. Now, this one doesn't do anything, just recursively call this. The partition is the key. So how to implement partition? Again, it's very similar to what I've done before. I guess, you can set low equal to begin. Okay, and high is end. Then pick the middle element as a pivot point. I know the difference here. I know the pivot point is what type is it? You can use auto, or it's a string, right? So pivot point is a string because it's a bits low plus high minus low divided by 2 dot title, right? I'm going to compare title, and title is a string. Okay, and you have to implement, not implement, include the string as well. Don't forget string. All right, so now you can use the string. So what we have, okay, so now you have a while loop, and again, it's very similar. It's low if it's title, right? Remember, is compare pivot. This is a string, right? If the string is less than 0, that means it's less than that's fine. You just keep moving to the right, and I think the same thing holds for the high. This time is greater than 0, then plus minus high, because high is from the right to the left, right? All right, so until these two are not holds, then we can swap. But remember, low has to less than high. That's the condition, and I'm gonna call swap. The best thing is that you can just swap these two objects, and because you're swapping pointers, doesn't matter. That's easier. Okay, now I swap it, and don't forget, this is key. You have to continue move the high and low point until they meet in the middle, right? Or they cross each other, and then you can return. Wait, is that? Wait, this is the while loop. Oh, okay. Return, not return 0, return high. Okay, so here you go. Let's run it. Let's make clean make. All right, so make sure you run this. Let's just do ebid.csv. It's a big data, right? So now let's do load. I'm gonna do quicksort. Look at how quick it is, 0.04 seconds. Versus if I do selection sort, it's still very slow. So here you go. It's and then you can display the port after sorting. You can see it's alphabetically sorted. That means your algorithm is correct. Okay, so that's all for module 2's assignment. Good luck with coding. And if you have any questions, especially when you want to compile it, you can, it depends on your machine, you may have a different compiler, and hopefully you can set up your environment already. If not, then shoot me an email or ask question away in discussion, or you can just Google it, Google your IDE, say VS Code or Eclipse, and with your machine, Mac in Linux or Windows, all right? And typically you will have those answers for you. Okay, all right, sounds good. Good luck, bye.